Anything for us to do this afternoon? Happy to answer questions. Can you hear me? Anybody there?
Esther, can you hear me?
Yes.
Okay. I know it seems a bit rudimentary, but I'm having some trouble with the first question from today's homework. It has to deal with rational numbers.
Okay, hang on a second. Let me just pull up the homework sheet.
Sure.
So which section was that? Which problem?
Section
Number 1?
Yes, number 1. It has to deal with prove that the set of negative rational numbers is not a group.
Well, for one thing, it's not closed under multiplication. So if x is negative and y is negative, then xy is positive. So if you look at the set of negative numbers, it's not closed under multiplication. So to begin with, there's not even a binary operation on the set.
I see.
Right? I mean, a group has some high binary operation, addition or multiplication. That means if you take two elements of the group and you multiply them, you stay in the group. But if you take two negative numbers and you multiply them, you don't have a negative number. So there's not even a binary operation.
I see. Thank you.
Sure. Anything else? Happy to answer questions.
Professor,
same section, question 4.
Prove that 1 and -1 are the only generators of the cyclic group Z?
Yes.
Sure. So what does it mean to be a generator of a group? So you say that an element A is let's say we're in an additive group, is a generator of an additive group if every element X in group, every element X in the group is of the form n times A for some integer A. In other words, G is the set 0 plus or minus A plus or minus 2A plus or minus 3A and so forth. So of course, A equal 1 generates Z because every integer n is n times 1. And A, or n times A is equal to 1. A equal -1 generates Z because every integer n is minus n times A. That's minus n times -1. If A is, so A equals 0 is certainly does not generate because the set of all multiples of 0 is just 0, which is not the set of all the integers. And if A is an integer not equal to 0 or plus or minus 1, then the equation 1 equals n times A is impossible, right? Because absolute value of A is at least 2, and A does not divide 1. So +1 and -1 certainly generate. 0 doesn't. And if you take any number like 7, well, multiples of 7, you don't get a 1 in there. So it's not the case that every integer is a multiple of 7.
Professor, are you taping?
Yes, I am.
Thank you.
Any other questions?
Professor, I think number 6 follows the same process that you just did with number 4, but would you mind walking us through number 6 too?
Okay, so 6 is to show that something is a generator. So problem 6 is to show that the number 1/2 generates the multiplicative group of powers of 2. And the proof is simple enough. 2 to the k is 1/2 to the minus k. So every power of 2, I mean, this group is just this group of all positive and negative powers of 2. So every power of 2 is also a power of 1/2 by this formula, positive and negative powers.
All right, thank you.
Mhm. Any other questions? Well, I can explain a little bit more about permutations. So Sn, which is called the symmetric group, Sn is the group of permutations of just the first n positive integers. And any permutation sigma is in Sn has the standard representation, standard way of writing it. Just make an n by 2 matrix, and you put, so the first row is a number 1 through n. A permutation is a function. So wherever 1 goes, 2 goes, 3 goes, and so forth. That's the standard form of writing a permutation. So for example, if you take 1, 2, 3, 4, 5, 6, 2, 1, 5, 3, 6, 4, that permutation sends 1 to 2, 2 to 1, 3 to 5, 4 to 3, 5 to 6, and 6 to 4. Okay? So this is just a nice example of a permutation. Now there's a special kind, and maybe the simplest permutation, is called a transposition. So a transposition interchanges two numbers and leaves everything else, every other number, fixed. So for example, in S6, the transposition, or the permutation sigma equal 1, 2, 3, 4, 5, 6. Let's say this permutation just interchanges 1 and 2. It sends 1 to 2, 2 to 1, 3 to 3, 4 to 4, 5 to 5, 6 to 6. The only element that doesn't stay fixed, the only elements are 1 and 2, and they're switched around. And the standard notation for a transposition is, for example, in this case, it would be 1, 2. So not a 2 by n matrix, just a pair of numbers. So in Sn, the transposition, let's say AB, sends A goes to B, B goes to A, and C goes to C for every C not equal to A or B. So as an exercise, let's say we're in, let's say in S6, compute the product of two transpositions. Suppose you have the transpositions 1, 2, and 1, 3. Let's figure out what that does to an element. So let's call this tau. So what is this permutation tau? If we write it in the standard form. So these are functions, so they operate on the right. So this tau, it sends 1 to 3. This sends 3 to 3, so 1 ends up at 3. This sends 2 to 2. This sends 2 to 1, so 2 ends up at 1. This sends 3 to 1. This sends 1 to 2, so 3 ends up at 2. And 4, 5, and 6 are fixed points under this transposition, under this product. So 4 goes to 4, 5 goes to 5, 6 goes to 6. So the product of these two transpositions is this permutation. Okay. So in group theory, it's very important to understand transpositions and know how to multiply them, or understand permutations in general and know how to multiply them.
Can you go over that again just one more time? I'm sorry.
Which part? The multiplication? Or the
Yes, please.
definition of a
No,
transposition?
no, just the multiplication, please. Thank you.
So this is composition of functions. So it's like f is the function 1, 2. So f's a function. These are all functions from the set of the first n integers to itself. And suppose g is the transposition 1, 3, which is also a function. These are both functions from this set to this set. So I'm interested in what is 1, 2, 1, 3. So this is f composed with g, just like in calculus. So, for example, so this is what I'm calling tau. So what is tau of 1? That's fg of 1. This is composition of functions. So this is f of g of 1. G is this transposition 1, 3. It sends 1 to 3. So g of 1 is 3. What is f of 3? Well, f interchanges 1 and 2 and fixes 3. So f of 3 is 3. So when you compose these two transpositions, 1 ends up at 3. 1 ends up at 3. For example. It's no different from what you do in calculus when you're learning the chain rule. To differentiate composite functions, you understand what a composite function is. And a permutation is a function, and the product is just composition of functions. So this is a transposition. It's the simplest permutation. The next simplest permutation is it's almost like a transposition. It's something that's called a cycle or a cyclic transposition, a cyclic permutation. So a cycle, which is a cyclic permutation, it has the following property. It's like you have a circle, like you might have 1 goes to 2 under this permutation. 2 is sent to 3. 3 is sent to 4, and 4 is sent back to 1. So you can actually picture this as a circle. If you were, let's say this is the permutation in S6. 1, 2, 3, 4, 5, 6. If you write this in the standard form, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes back to 1, and anything not in this circle of numbers stays where it is. 5 goes to 5, and 6 goes to 6. And the numbers don't have to be 1, 2, 3, 4 in order. You could have 6 goes to 3, goes to 5, goes to 2, goes to 1, goes to 6. That's a cycle. This cycle has length 4 because there are 4 numbers around the circle. This cycle has length 5. And if you were to write this in standard form, see, 1 goes to 6, 2 goes to 1, 3 goes to 5, 4 is not here, so 4 goes to itself, it doesn't move. 5 goes to 2, and 6 goes to 3. So these are the standard representations of these cycles. Usually for a cycle, you also write the cycle as just a single like string of numbers. 1 goes to 2, goes to 3, goes to 4 is this cycle. This would be 1 goes to 6, goes to 3, goes to 5, goes to 2. That's a way to represent this cycle. Now, and it's the same permutation no matter where you start, because you could just as well say, this is the cycle, 3 goes to 5, 5 goes to 2, 2 goes to 1, 1 goes to 6. But this is the way you generally write a cycle. It's just a sequence of numbers, and you understand that what it means. So if you have 2, 5, 4 as a cycle, that sends 2 to 5, 5 to 4, 4 back to 2. And if you wanted to write it in the standard way, 2 goes to 5, 5 goes to 4, 4 goes to 2, and everything else goes to itself. So cycles are sort of, I'll explain to you in a minute, they are in a certain sense the building blocks of all permutations. But a cyclic permutation it's almost like the simplest thing you can imagine. You just have numbers. If you think of it as numbers in a circle, it's like you're moving around the circle. Each number goes to whatever comes next in the circle. And anything not in the circle doesn't get moved at all. And one of the basic theorems about permutations is you can decompose any permutation as a product of cycles. So let's say we're in S10. So I don't know, I'll just write down a permutation at random, 8, 5, 2, 6, 1, 9, 3, 10. What numbers haven't I used? 4, 7. So there's some permutation of the numbers 1 through 10. Let's take a look at this. The number 1 goes to 8. The number 8 goes to 10. The number 10 goes to 7. The number 7 goes to 3. The number 3 goes to 2. The number 2 goes to 5. The number 5 goes back to 1. What numbers haven't we used here? Well, we haven't used 4. Let's look at 4. 4 goes to 6. 6 goes to 9. And 9 goes back to 4. So this permutation, let me call it sigma. Sigma really is like it decomposes into 2 cycles. You have the cycle 1 goes to 8, goes to 10, goes to 7, goes to 3, goes to 2, goes to 5, times the permutation that sends the cycle that sends 4 to 6 to 9. So I can take this permutation and it decomposes into, these are cycles, but in fact they are disjoint cycles. That means the numbers here are different from the numbers there. So an extremely important fact, there are 2 fundamental facts about permutations. One is that every permutation decomposes into a product of disjoint cycles. And this is essentially unique. It's like factoring numbers into a product of primes Well, here we're factoring numbers into disjoint cycles. And it's always fun, given a permutation, to decompose it into cycles. So let me just show you another example. Suppose we take a permutation 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Wow, that's big. So this is going to be a permutation of the numbers 1 to 15. I'll just plug in numbers more or less at random. I don't know. We'll see what happens. See what's some numbers I haven't used. I haven't used a 4 or a 6. I haven't used a 3. I have 1, 2, 3, 4, 5, 6, 7, 8. I haven't used a 9, 10, 11. I haven't used 12. So I think I've used every number here exactly once. So this really is some permutation sigma. This is in S15. This is a permutation of the numbers 1 to 15. I don't seem to have the number 14. Maybe I used something twice. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, I have 2 6s. So I'll make this a 14. Okay, so now we have a permutation. So here is the problem: write sigma as a product of disjoint cycles. So let's just start with 1. We can start anywhere. 1 gets sent to 5. 5 goes to 15. 15 goes to 12. 12 goes to 14. 14 goes to 9. 9 goes to 8. 8 goes to 2. 2 goes to 7. 7 goes to 6. 6 goes to 13. 13 goes to 3. 3 goes to 10. 10 goes to 11. 11 goes to 4. And 4 goes back to 1. So it turns out, you couldn't tell just by looking at this, but this permutation really is a cycle. It's a cycle of length 15. So that's what it is. Are there any questions about how I did this calculation?
No, but if you were to ask how to write that as a product of 2 disjoint cycles.
So it's a product of 1 disjoint cycle. So it's just, they're only 1.
Okay, thank you.
Yeah, let's do another example. Suppose I take the permutation. So let me just try. I'm just doing these numbers at random. Oops, you can't use 7 twice. Let's see. So what I have 1, 2, 3, 4. I haven't used 5, 6, 7, 8. I haven't used 9, 10, 11.
Professor, you used the 9 under the 8 originally. You have used 9.
Oh, okay, thank you. So I'll put a 9 here. Let's see, what am I missing? I'm missing 12 and I'm missing 14. 1, 2, oops, I have 2 2s. Oh, this is supposed to be a 12, I think. Okay. Let's see if this really is a permutation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So before I do it, I'll give you a chance to write sigma as a product of cycles. It could be this is just another 15, a cycle of length 15. If not, it's going to be a product of 2 or more cycles. Anybody do this? Sort of curious, how many cycles did you get?
The first cycle is just 7 and 1.
Excellent. So 1 goes to 7, and 7 goes back to 1. And again, you can start your next cycle with any number you like. It doesn't have to be 2. I mean, I always take the next smallest number that hasn't been used, but there's no reason to do that. 2 goes to 8. 8 goes to 12. 12 goes to 3, and 3 goes back to 2. So that's a cycle of length 4. 4 goes to 11, goes to 15, goes to 14, goes to 9, goes to 6, goes to 13, goes to 5, goes to 10, goes back to 4. And we've used up all the numbers. So sigma is a product of 3 disjoint cycles of lengths 2, 4, and 9. This is cycle of length 2, or a transposition. This is a cycle of length 4, and this is a cycle of length 9. And of course, they have no elements in common, and these numbers have to add up to 15. Of course, every number has to occur exactly once. Okay, any questions about this? Let's do one more example. Suppose I take the permutation, let's say in S7. So there, oops. I think I've used something twice. That's better. So if I write this as a product of disjoint cycles, 1 goes to 2, 2 goes to 4, 4 goes to 5, 5 goes back to 1. 3 goes to 3. I can write that as a cycle of length 1. And 6 goes to 7, and 7 goes back to 6. So this has length 4, this has length 1, this has length 2. I don't really need to write this. I could leave it out, 3 goes to 3. But this just emphasizes the fact that the product of the lengths of the cycle has to equal 7. Okay. Okay. So there are two facts about permutations that are fundamental. The first is, just like every number is uniquely a product of primes, the order can be changed, but the product of primes, every permutation is uniquely a product of disjoint cycles. And you can rearrange the cycles because disjoint cycles as group elements commute with each other. But what's extremely interesting is, in fact, if you want to understand permutations or write permutations, you never have to do anything other than use transpositions. Just those little permutations that interchange two things. So let me give an example. Suppose I take the cycle of length 3, 1, 2, 3. So 1 goes to 2, goes to 3, goes back to 1. I claim I can write this as a product of two transpositions. They won't be disjoint, but it will be a product of two transpositions. So I could take the transposition that interchanges 1 and 3, and the transposition that interchanges 2 and 3, I think. Let's see. 2 and 3. So this is a 3 cycle. And here I have 2 transpositions. Let's see. What is this? What is the?
Professor, I'm sorry to interrupt. Is the order important? Because you've written 2 is sent to 3, but 1 is not sent to 3. 3 is sent to 1.
No. In it, where? Here or here?
No, in your cycle in the circle that you drew.
No, in the cycle, 1 goes to 2.
Right.
2 goes to 3.
Right.
3 goes back to 1.
Right.
Yeah.
So 2 goes to 3. I see the first one.
Well, no, forget this.
Oh, okay. Never mind. Thank you.
This is a 3 cycle. 1 goes to 2,
Yes.
2 goes to 3, 3 goes to 1.
Okay.
And I claim I can write this as a product of two transpositions, namely 2, 3 times 1, 3. So if I examine the transposition 2, 3 composed with 1, 3, what does that do? It sends 1 to 3 to 2. This sends 2 to 2 to 3. This sends 3 to 1. This sends 1 to 1. So when I compose these two, I have 1 goes to 2, 2 goes to 3, 3 goes to 1. So this is a correct formula. Okay. So every 3 cycle can be written as a product of two transpositions. And there's nothing special about 1, 2, and 3. If I have the cycle A, B, C, A goes to B, goes to C, goes back to A, I claim this is the same as the product of the transpositions AC and BC. This sends A to B, B to C, C to A. Yeah. So every 3 cycle that's a cycle of length 3 is a product of two transpositions. Oh, I should say one other thing about cycles, just for the record, and then I'm going to stop. Suppose I have a cycle, let's say I just write it as A1, A2, A3 up to A sub L. So this is a permutation that sends A1 to A2, A2 to A3, and so forth. What is the inverse? It's another permutation. It reverses it. Just write this backwards. AL goes back to AL minus 1, goes back to AL minus 2. A3 goes to A2. A2 goes to A1. So this sends A1 to A2, and this reverses it. A2 goes back to A1, and so forth. So if you have a cycle, you can write down its inverse in the group just by writing the cycle in reverse order. So if you have sigma is the cycle 1, 2, 3, then sigma inverse is 3, 2, 1. Which is, if you like, is the same as 1, 3, 2. Doesn't matter where you start. 3, 2, 1, 3, 2, 1. Yep. So, okay. That's all I'm going to talk about now, but permutations really are very interesting, very important. And permutation groups are very important.
Thank you.
The two most important classes of non-abelian groups are the matrix groups we talked about and these permutation groups. Okay, we will quit for the day. I'll be around tomorrow morning again at 11 o'clock. Bye.